All right, I'm back from lunch. Ready to continue working on this allocator stuff. We were discussing alignments before we took a break here. I would like to learn more from the man page if I can find it. Max align T. Hopefully it was a man page. No. Let's see here. So he asked it to explain the union trick, which is something that the book is using to make sure that this header is aligned appropriately on a specific boundary. So let's just take it from the beginning. The union trick is a way to force a block of raw bytes to have the maximum alignment required by the platform. It works because a union's alignment requirement is the maximum alignment of its members. That makes sense. So if you have like an integer and a char, and your max alignment in this case is 16 on this platform, then you would just add this max align T, I guess, and it'd be like, okay, that requires 16. The weird thing is, though, is that max align T has a size of 32. I guess that's where I'm like kind of like weirded out, is I don't really, I guess I need to take a step back here and say, let's do a new chat here. Just say, explain the difference between, actually, no, I just don't like ChatGPT all the time. Let's just Google for size of versus align of. Actually, we have the freaking reference manual here. Let's just go to the reference manual in the book. Let's see if there's an index here, align of. Let's see. Array, alignment by union, alignment restriction. There is no align of. So it must not have been part of the language when this book was written. So I think it's fine to, oops. Not that. Please go away. Control Shift T. There we go. I think it's fine to pull it up here on Stack Overflow. What's the difference between size of and align of? Define size of align of T. Okay, this is C++. And oh, that's just a convenience to do a size of, to standard out / align of. His all came out identical. So I can understand the struct being a larger size than its alignment. That makes total sense. But this union, if the union is going to be smaller than 32 bytes, and it has alignment of 16, we really only want it to be 16 bytes, because then it would be 16 byte aligned. That makes sense. Let's see, max align. Yeah, this is what I got here as well. So we have a character array of 4. It's not known that A begins on an odd or even address. Soon a line of int is equal to 2. So then we say, hey, A, I'm going to dereference or store into some pointer P. No, sorry. We have an int pointer, and it's going to point to the same place as the array here. I don't understand this. Assume a line. I don't understand this example here. I would assume the compiler would align that properly, but I guess it doesn't. Okay. Okay, so I understand the operators now. I want to understand what the hell is max align T. That's standard. I want C. C23. Please go away, ads. So annoying. That's why people use ChatGPT, Stack Overflow. Jesus Christ, these are standard nerds. Let's go back here. All right. Yeah, it'd be 1024 because it's a power 2. I don't know how it'd be less. I don't know why they called max here, because I don't know how it'd be less than 1024. Could be more, but because it's a power 2 and this is likely a power 2, I think it's fine. Align as max align T unsigned char buffer without a union. I like that. Let's do that. So let's open up our allocator. So we got this union thing and we're using this unsigned size. No, sorry, this max align T here to ensure alignment. But we can just pull this out and say, hey, you're in header. Blow away that. This will just be a header, struct header, pointer. And we'll use align as, which I'm not super familiar with. But I think it goes here. Well, what we'll do is we'll bring back what we had before here. I'm going to do the line of all of these things. So size of, line of, oops. What? Okay. So H is the header, and then H.S is the struct inside the header. And then I guess we could do H.A here. Oops. And what that'll do is give us the max line T, so we don't really need this thing anymore up here. And then we have the pointer inside the struct, and then that. Okay, the size of the whole thing is 32, and that's because we're unioning between a 16 byte and a 32 byte value. But really, we just want to do the 16 byte value. So yeah, this is driving the size here along with the alignment, which is good because you want to be 16 byte aligned. I think being 8 byte aligned why are some types like 16 bytes? I guess 8 alignment. We want this thing to be 8 aligned. So let's go back here. I am creating an allocator for 64-bit for AMD KTOR for, is it 1L? Oh, it's 2 L's. For AMD 64, I want it to be to provide memory at a base address that is 8 byte aligned, since it is a 64-bit machine. How would I go about making sure the address I give it is 8 byte aligned? What's this valloc? I think POSIX memo line is the right one. Yeah. Oh, SSC types. I guess there's a long double too. Yeah. There's 128 bit types, yeah. What's it called? Max. Fuck. Align T. What are these SSC values? Okay, that means that 128-bit values don't need to be 32-bit aligned. 32-byte aligned. Okay, let's read through all this. Oh, sorry, I got a message. Okay. All right. The question that I wanted to have answered is so does that mean that 128-bit values, bit SSE values on AMD 64 do not need to be 128-bit aligned, only 64-bit? Wait a minute. 8 bytes is 64-bit. 16 is 128-bit. 32 is how many bits are? Jesus Christ. Sorry, my math is off here. 128 bits divided by 8. 16 bytes. Yeah. So if you do 32 bytes times 8, 256 bit. I don't think I've ever seen a value that big. I guess y is size of max align t, the value 32, which would imply a size of 256 bits. Are there values why is size of max align t on AMD 64 the value 32, which imply a size of 128 bits? Are there values that are that large on the system? And would they have the alignment of 16, since 16, which is 128 bit, since align of max align t is 16. I'd rather just do the padding. I guess the union thing. I don't know. I need to look up this align of thing. So we say C align of, not align of. What was it called again? There's an example here that they gave. Okay, I can't find it now. It was like underscore align. Align as. Oh. There's an align as. Instead of doing the underscore. Okay, I'll come back to that. Sorry. Let's go back down here. Close out of that. What is static assert? This is a compile time assert. I thought you put the name up here. Oh, it's because they're doing a type def. Okay. Align as. So we create our struct header, size and flags. It's gonna have a pointer. To the next block, and then a size. So 264 bits. So it's going to be 16 bytes. Your header is 32 bytes. Uh, 32 is not 120 bit. It's 256. Okay, we'll try that. Okay, we'll come down here. We can just say static assert. Damn, C's gotten awesome. So down here, I'm going to say static assert that the size of the header, struct header, I'm going to call it a struct here in a bit, is equal to 16, and its a line of is also struct header. This is going to be a struct header, max align, don't care about that, and struct header pointer, and the size will just be a, yeah, unsigned. It's fine. So this is going to be 4 bytes. This is going to be 8 bytes. 9, 10, 11, 12. 12, and then it's going to be aligned to 16. Why can't I do that? And then this would be a struct header. Don't care about that. Did I not? Let's just copy these, and I'm gonna quit. Jobs. Pull this down here. Alright. Vim allocator. Okay, this is what I wanted. Do the static asserts. Convert this back to a struct header. Delete all this stuff here. We're gonna have a struct header pointer. It's saying that the we don't need any of this. There we go. Make what is the line of the header then? Make line of is 8. I want the line of to be 16 though. I really like these static asserts. Can I do it here and say align as, and then, sorry, please go away, Lysium. We're gonna say align as, what was this? Max align T? Yeah. So that still doesn't like it. How do I align this struct definition to 16? To get the assertion to pass. I'd say struct align as, struct align as like this. That doesn't work. No. Okay, just tell me the right syntax. It has to be at the end. Okay. I don't care where it goes. I just want it to do it. Okay, ChatGPT is being literally idiotic here. Is there an example here of using a line as? So you use it at the place where you declare declaration syntax, not in the function definition or type definition. Give me 1 second. I gotta go grab something. All right. Appears in a declaration syntax is one of the type specifiers to modify the alignment requirement of the object being declared. Okay, so that's not the thing that we want. Okay. So maybe the union trick is the right thing. Oh, yeah. That wastes a byte though. Yeah, I would like this a line of to be. It looks that align as does not work the way that you think it goes on the field, but you can't align an entire struct. I guess what we could do is say align as on one of the fields, and that will guarantee the alignment of the whole thing, right? It doesn't appear that you can use align as or align as on the entire struct itself definition. They're still saying that you can do it as part of the type def here, but I don't think you can. Call this underscore header, and then we'll like type def align as max align t, and here we'll say struct underscore header. That doesn't work. We'll try underscore align as. That doesn't work. I think what we need is like a char. We'll call it underscore 0. And this thing will say align as max align t. Oh, we need to fix our header name now. So you back that out. Hey, look at that, that worked. I like that. And then we'll just do a little comment here that says forces alignment. Okay, we'll do two assignments. So he says size of the header is equal to the align of the header, and the align of the header is equal to the align of max align t. Make build allocator. So size of it is 16. So that's 264-bit, that's 120-bit value. And the pointer is 8 and the length is 4. What is the appropriate type for a native sized integer in C? For example, 64-bit for int for AMD 64 and 32-bit for x86 32. Size t, unsigned integer type returned by size of, used for object sizes and array indexing. It's architecture dependent. Unsigned long 64 bits, 32 bits. Okay, we'll do a size t here. Make. Now when we run this, should still have the same size and alignment, but both fields should be 8 bytes. Yep, perfect. And since we're on a machine that can target 32 bits, let's just rip grep for underscore 32. Yeah. Chapter 01 makefile had some stuff in here for 32-bit compilation up here. No. Yeah, down here. Bam. Oh, it uses XCC. Okay. I was gonna say cd back into that directory, vim up or foreground. So we're not gonna have to mess with that right now. Let's close it out, and we're gonna vim up makefile, and we're gonna paste this thing in here, and this thing we're gonna call allocator 32, allocator 32, allocator.c, and we'll just say same flags. We'll give it the standard equals C23. Everything else is the same. And then up here, I'm going to have to add the build allocator 32. Yep. So now I'm going to make, of course, it's going to give me a bunch of warnings. Long, unintended, yeah, I don't care about those. Build. So now when I do build allocator 16 and 8, so allocator 32 should have 8. So the size of it should be size of it should be 8, and each field should be 4, and the alignment should be, I believe, 8. Let's see. Yeah. Okay, that's correct. Okay. Ooh-wee. Okay, so that got us what we needed. So now we have our header. And I'll leave these things here for now, and we'll continue on with the reading. I'm done with you. Done with align as. Align as is nice, but you can only do it on a specific field. And if I did this, you see how my static assertions field? No bueno. Oh, that's nice. Well, let's go ahead and jump over to learn log. I'm gonna come back to this. What is it? Blogs, I guess. We'll put it down here at the bottom of the queue, and this will be here, and we'll just add. There we go. Get push, push all. There we go. Size of, let's go ahead and ask ChatGPT, see if it can figure this out. Why is size of max the value 32, which implies size of 256 bits? Oops. I didn't copy the whole thing. Quit. I guess if you have a bit of memory that is the size of a max align T, you can align in that memory without influencing anything around it. I guess that's why they have 32 bytes there. Okay, that mystery solved. Close out of that. Close out of that. All right, we're back to the book. All right, so we have our header. It forces alignment of the blocks in a different way than was. Let's pass this into ChatGPT and say, is there a better way to do this? I don't like that. This doesn't work. So you're full of shit. Good job, ChatGPT. Let's do Gemini. I've heard of this, the flexible array member. But it's not a variable size structure. It's just it's a zero sized field. All right, I'm gonna say start. So you malloc size of header, which is just the size t, plus the size of, where the hell is long? That code is wrong. Yeah. Well, I'm implementing malloc. I can't use malloc. Alright. I'm done reading about that stuff. Using flexible array members. Okay. All right. So we don't need to do this little union trick. But let's read through it just so that we're aware of it. So we have a type def long align. And I guess a long is the largest value at the time of writing this. I guess long wasn't a thing. Then we go into a union header, which is the struct that is actually the header, with an align X to force the alignment, and then we just don't use the union. Then the struct, we have our header pointer and our size. The line field is never used. It just forces each header to be aligned on the worst case boundary. In malloc, the requested size in characters is rounded up to the proper number of header sized units. The block that will be allocated contains one more unit for the header itself, and this is the value recorded in the size field of the header. The pointer returned by malloc. So I guess we should do a malloc. If we do man malloc, they come from standard lib, so I need to say something like, what did they call it here? They call it malloc. Maybe we can undef malloc? Pound undef malloc? You're not understanding me. Hello, hello, hello. I think I had my mic muted. Yeah, I got a segmentation fault. I'm gonna take a quick break. I'll be right back. Okie dokie. All right. So we core dumped. Let's just run GDB. So it's in libc. Oh, because printf also calls its own malloc. No, quit, please. Yes. That makes sense. Let's just do it right here. Right to standard out, file no. We'll do standard error. And then we're gonna write S, and this will be strlen of S. Unix standard.h. Undeclared library function strlen. So this is primary string. There we go. There we go. And I need to add a new line here. Malloc called. Get back now. Okay, so we're calling our own malloc. That's all I wanted to test there. So I can get rid of these two now. Okay. And then we're gonna need a free. I think it's like this. Maybe it's an int. Free void star p. I think that's man free. No, man 3. Yeah, it's a void. Okay. Okay. So we have our malloc and free defined. In malloc, the requested size character is rounded to the proper number of header size units. So the first step will be in malloc, we want to do that rounding. In which case we say size mod we should also define this constant here. Define header alignment. This will be align as header alignment type. Size of, align of, this is going to be align of, and then this will be header alignment. Oh, this is recursive, so it needs to be header alignment type. There we go. This will be mod of header alignment, not the type. Size. Not equal to 0. Then size plus equals. I guess we could just do that outside. We don't need to do a branch. So we take the size, we mod it by the header alignment. That's either going to give us a remainder. So say we're at 16. It'll give us a remainder of 0. We don't have to add anything. But say we're at 15. This is incorrect. This needs to be the header alignment. Oops. Minus size mod header alignment. Oops. Please go away. There we go. And then we can delete this side. So we're going to add on the alignment subtracted from the remainder. And I'm not going to print f here, but I will write out to standard error the value. We need Unix standard, not h here. We're going to write out the value, the buff, len of buff, something like that. We'll just say 1. Might not be 1. So how do we get this thing written out? Size. Size len size t, or len of size, both would work. Sorry, size of. New reference to it. Yeah, I'll just ask AI here. Implement a function that can write out numbers to standard error without using NC, without using printf, the standard library. $32, because we're at 17 here. If I went to 32, $48. I feel like that's an off by 1. Yeah. $33, what the hell? So header alignment is 16. So let's just test this out here. So for auto I is equal to 0, I is less than, we'll say 35, I plus plus, or the cool kids do plus plus I. And then we're going to auto tester malloc I, printf it out. Oh, typo. Zero, you should get a 0. So I thought this was going to be the solution. Size minus 1 here. but it didn't. There we go. Just lost his damn mind. So here we compute the non-aligned bytes. So we take the size, we subtract 1, then we modify header alignment, and then we subtract 1 from that value. And then we have our header alignment that we subtract the non-aligned bytes from to get the extra padding, and then we add that to the size. I'm just doing this to give these fragments names. Obviously you can do it in one big expression, but it's nice to break it out like this. This is the thing I'm trying to figure out. Is like, normally I just do like size mod header alignment, right? But the problem is that it's not 0 addressed, it's the size. So you have to do it, it's off by 1, so you do -1. And then we say our U header alignment. What the hell? That ain't right. Okay, the math got fucked up somehow. Somehow, we messed the math up. We had the right answer, and then we messed the math up. So, let's focus on this expression here, which is clearly wrong. So 0. So we're saying 0 minus 1. And size is of size t, which is unsigned, so you wrap around to its maximum value. But let's just say 1. Let's just do what you're doing before, which is just this. Make build allocator. So it's off by 1. So you can always just subtract 1 from this. Of course, that gets you the negative number territories. Well, this is the non-aligned bytes, right? because when you have one byte, that byte is not on a byte boundary. When you ask for 16 bytes, it's 0. So yeah, this simple statement here, non-aligned bytes, that is correct. Now, what you need to add to it is going to be the header alignment minus those non-aligned bytes. So if the header alignment is 16 and you're good, then you're going to be having extra padding of a whole byte, which is not good. So this whole thing you need to then mod against header alignment again. Fifteen, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yep, that's exactly what we want. Now we have our padding. We'll then say size plus the padding is what we're sending out there. There we go. There we go. I'm sure there's an easier way of doing this. Let's see. I forget what they call it. Inlay hints, yeah. Okay. So you just space li, space L would be lazy. No. Please stop. Space code. D. Code. S. Oh, this is cool. That's pretty cool. So, oops, my bad. Code S. Okay. UI H. There we go. UI H. UI H. UH. UH. Okay. So we got these right. So I'm just going to comment them out so I don't have to deal with this stuff. Okay, so these are the non-aligned bytes. This is the extra padding where we subtract off the non-aligned bytes and then mod it by itself. Is there a better way of doing this? Let's just ask ChatGPT. Simplify this expression in C, and it'll be x minus y mod x. So the negation of y, is that true? Okay, it says it's true. Okay. Maybe we can take the negation of size. Yeah, that works because mod is not a remainder, it is modular, which means it gives you back that high order. Okay, that works. So negative size, we just flip it into the negative, do the mod on it. Oh, the size is not signed. So auto padding, I'm curious what that comes back as. So we do here, what is this? UIH? Yeah, it comes back as an unsigned long. If I just do 12 here, it comes back as size T. Unsigned long. Padding. Okay, that worked. So we take the negation, we then mod it to get how many bytes that we need to add, and then we add them. And if I run this again, make everything looks good. Yep. Okay, I'm just gonna get rid of this stuff. I don't think it's needed anymore. Definitely don't need this. Okay, make looking good. And if I do it on the allocator 32, so that got us why does it say 1024 here? Printf. We'll just say P here, auto P, that makes that clear. And we'll just do it like this. Why is there 1024 in front of it? Is what I don't understand. I is equal to 0. 1024 doesn't exist anywhere. Here, we'll just print out the I's. It still prints it out. We'll do 2 printfs. Still 1024. Which means it's happening sometime before main. Otherwise, okay. What is this, that 24 thing popping out of? Oh, it's because our rights are not flushed here with the D. So we have to say printf and then F flush. Standard error. F printf to standard error. F printf to standard error. Semicolon there. So you have to do a flush here because we don't have a new line there and it's a line buffered. Okay, make. There we go. There we go. And then if we do it on an allocator 32, so we went from 0 to 16 to 32 to 48. 0 to 8 to 16 to 24 to 32 to 40. Yeah. That seems right. Okay. All right, continuing onward. In malloc, the requested size and characters is rounded up to the proper number of header size units. Did that. The block that will be allocated contains one more unit for the header itself, and this is the value recorded in the size field of the header. Wait a minute. The pointer returned by malloc points at free space, not. Okay, so we have to go here and say, hey, bytes to allocate needs to also contain the size of header. Okay. Okay. Let's do our UH. Bam. Look at that. All right, man to S Bork. All right, let's continue reading. The pointer returned by malloc points to the free space, not at the header itself. The user can't do anything with the space requested, but if anything is written outside of the allocated space, the list is likely to be scrambled. A size field is necessary because the block controlled by malloc need not be contiguous. It is possible to compute sizes by pointer arithmetic. The variable base is used to get started. If free p is null, as it is at the first call of malloc, then a degenerate free list is created. It contains one block of size 0 and points to itself. Well, it can't be 0 because it's okay. Let's take this thing off then. Call this thing block size. In any case, a free list is then searched. The search for a free block of adequate size begins at point free p, where the last block was found. The strategy helps keep the list homogeneous. If a too big block is found, the tail end is returned to the user. In this way, the header of the original needs only to have its size adjusted. In all cases, the pointer returned to the user points to the free space within the block, which begins 1 unit beyond the header. Okay, let's look at the code that they wrote here. So we got some code on 2 pages, and then we're on our own. So the first thing they do is they use this global. They call it a static header pointer free p set equal to null. So a static struct. I think I might type def this thing. They're talking about type defing it. Yeah. So anywhere that struct is used here, would say type def this thing as header, and then struct header I do need that. Okay. It just cleans it up a little bit. Okay. So he has his base, empty list to get started, a free list. Okay. So where do we call break? more core. More core. There's more core thing, which is implemented here. And that calls S break. N units. Okay. So in this malloc, give me 1 second. I think what I should do is read this code, fully understand it, finish reading the chapter, and then go back and do my own implementation. That way, at least at the end of the day, I can say I finished the book. Even if this this doesn't go very well. Okay, so we have a header pointer, 2 header pointers, P, and a previous VP, a previous P. And then we have this function called more core, which we can give it a number and it gives us back a pointer to a header. And then we have this counter called N units. Now N units, he computes the N units by saying, grab the size of the header plus the number of bytes requested minus 1 divided by the size of header plus 1. Now, let's do a little Python here because I want to see what this thing results as. Python, this is their expression, units. Def N units takes in a N, and it computes, what is this? N plus, in our case, 16 minus 1. And then all of that divided by 16 plus 1. Okay. So we got N, 16 minus 1, and then 16 plus 1. And my, I'll call this def M units, M for my, return. So what I took was negative N mod 16. So that computed padding, and then we'll say N plus that. N plus negative N mod 16. Oops. And then I'm just going to say for X in range 10, we'll do 35. Print N units of X space and M units of X. Oh, I messed that up. So this needs an M. I don't know why I decided to change it. There we go. Okay, well, his is going to be in Python land a little bit strange. Because it's not using integer division. So let's switch that to be integer division. Oops. So I'm already at the number of bytes. And this guy's off here. I guess if you compute it as like in addition to the header itself, he's correct. Yeah. So we went totally different routes to compute this value. But it's just effectively the same. So that's the number of headers. I did the number of bytes. He did the number of headers. I'll stick with mine because it's correct. Call that a line size because we're given size, compute the padding, now we have a line size. So these are number of blocks. So auto n headers, blocks, we'll call it blocks, is going to be equal to aligned size divided by header alignment. Does he go from units into bytes? His more core end units. Yeah, he has to do multiplication later. I'd rather just keep it in bytes, to be honest. So where else does he use n units? Let's see. Computes it here. His size is in units. I guess that to keep things consistent, keeping it in the unit size might be appropriate. Let's go back to what he was saying over here. So size. The requested size size and character is routed up to the proper number of header sized units. The block that will be allocated contains one more unit for the header itself, and this is the value recorded in the size field of the header. So size is not how many bytes. Size is because you need to allocate in these aligned units. Okay. So we compute the aligned size. Units is going to be aligned size divided by header alignment. Plus 1. we go back to our Python program here, I'll go ahead and modify my function called munits. So it's going to be m plus the negative of the mod, and then we're going to take that value. We're then going to do integer division on the header alignment, which we know is to be 16, and then we're going to plus 1. Oh, we need to take some parentheses here. So this has to be like this, maybe? Because you don't want to add that onto there accidentally. Yeah. Wait, what? M is the requested bytes. So we say, hey, we're going to take M plus the padding, which is negative M mod 16. Oh, we need to have the parentheses around here. There we go. There we go. So now we're very consistent. But if we look at our definitions for M units, and I have to go in the history now to look up N units. N units. Yeah, we're both doing this 16 plus 1 now. And I just did a little bit different math on the numerator. So if we write out our math here, I'm going to do it just on a margin here. So I have the numerator M plus negative M mod 16. So that whole thing is equal to M plus 16 minus 1. Which means that 16 minus 1 is equal to the same thing. is that possible? I don't understand how that's possible. M plus a negative M mod 16 which means that 16, which means we can cross out these m's and say 15 is equal to negative m mod 16. How can we know that for sure? To say mod is, we'll just do some test cases here. Say m negative 1, and we'll make sure our precedence is right. Mod 16, 15. Negative 2 mod 16 is 14. It's different. I'm pretty frustrated here. So we have these two functions that behave identically. I'm just going to put them down here. And I'll put out a little for loop as well. Okay. I'm just going to get out of the interpreter, clear state. They behave identically. So basically these two expressions are identical. So we can set them equal to each other. We could say, okay, that and that are the same. What we'll do is I'm going to hack on some of this, and I'm just going to make sure that they remain the same. So if I delete the right-hand operator on its integer division, we should have the same value, right? That seems reasonable. The right-hand value, 16 plus 1. I guess the modular applies first. Oh, okay, and then we add 1. But I think because they're in the same... yeah, I think they're the same, because the integer division applies of 16 applies first, and then plus 1. So if you take both of those operations off, it's safe. So let's go ahead. I'm going to kill you, ChatGPT, because you're not very helpful, and then do this. These are totally different values. Isn't that interesting? So the division by 16 is the thing that really, like, the integer division let's bring back the integer division 16. Those should be the same because it's just a plus 1 at the end, right? Oops, sorry. So because integer division, you drop bits. Yeah, those are the same. Okay, I just learned something, that even though you perform the same operation here, it doesn't mean that the values result of that operation is the same. Doesn't mean that you can eliminate the operation. Okay. So this was if we took these values and we divided by integer division by 16, we would get back 0, 0, 1, 1. Yeah. So I did a little bit more work here than they did. I mean, their equation's undoubtedly superior than mine because I'm saying, hey, compute the padding that you need to add on to this thing and add it onto it, and then divide by the size, and then add 1 for the extra header. Whereas let's think through like what they're saying. So they're saying is just add. If you add so we have a number and we're adding 15 to it and then divided by 16. Okay. So if we just added the size of and then did the integer division, say it was like 1, the value is 1, we added 16, we got 17, divided by 16, we get back 1. Hey, how's it going? Sorry. I got distracted. I'm working on a malloc, yeah. I'm trying to write my own allocator based on the K&R C book. And I got to this place where they have this expression here. And I had come up with my own expression to compute the size, and they came up with one that was better. And I'm trying to think through like why that's the case. Sorry I missed your chat there. I do need to get better at looking at chat. Just writing a memory. Okay. I'm trying to think through like why theirs works. So if they didn't do that math, if you just did integer division on n, it would give you 1 too few, potentially. So let's just do some like basic tables here. So say we request 0, 1, 1, 2, 3, 4, 5. These are different sizes. And say our header size is 4 bytes. So 0, we want to translate that to, okay, you're actually requesting 1. 1, you're requesting 1. 2, sorry, 0, you're requesting 0. My bad. 1, 3, you're requesting 1. 4, you're requesting 1. 5, you're requesting 2. So n is going to be equal to 4. And if we did this thing where we just say, take your size and do integer division by 4, by n, then what that would give us is, so size is 0 divided by 4 would be 0. So that's correct. 1 divided by 4 would be 0. Two divided by 4 would be 0. 3 divided by 4 would be 0. 4 would be 1. 5 would be 1. Oops. So, actually I should do this in like a second notes file. Let me just write this out. Vim temp. Okay, so then I can uncopy this out, which is nice. Boom. The problem with just doing the division and say how many ends do you need is that you're gonna have bad results here, where you're actually coming up one shy in a lot of situations. Pretty much all situations that are not evenly divisible. So what they do is they add on, they do s plus n minus 1, and then divide that by n. And what does that give us? Gives us s. S is 0, n is 4, so that's 4 minus 1 is 3. Divided by that is going to be 0. 1 plus 4 is 5 minus 1. 1. 2, 6, 5, 1. 3, 5, 6, 1. 4, 6, 5, 1. Is that right? 4, 6. So this is going to be 0, 4. Sorry, it's 4. 0, 4, 3, 0. 1, 4, 5, 4, 1. 2, 4, 6, 5, 1. 3, 7, 6, 1. 8, 7, 1. 9, 8, 2. So I mean, it clearly works, but I'm just like trying to wrap my head around like, why does this work? So what you're saying, oh, let me clear my chat. So what they're saying is like, take the size, and we're just going to give you a freebie. What happens if we just give you the freebie to give you an extra thing here? So that's going to be like this would be 0 plus n divided by n. The n just going to get blown away. And we'll be back to 0 plus 4 divided by n is 1. This would be 1 because it would be 5, 6, 7, 8 would then be 2. 2. Yeah, so it's basically like adding 1. But then subtracting that 1 shifts it down 1. Yeah, that's what happens. When we subtract 1 from there, on the numerator, the result gets shifted downwards. It's not how I would implement it, but it clearly works and it's more efficient. So let's Vim allocator. So let's re-implement this as the equation that they have, which is size plus header alignment Should we use header alignment here? Because it made sense here because we were trying to get things aligned. But here, we want to get into units, auto n units. Size plus the size of header minus 1. That whole thing, integer division, by size of header plus 1. That's not even what this is. This doesn't work as a sub-expression. It's a nonsensical value until you do the integer division, so I'll just keep it there as one statement. Okay. Malloc. Okay, let's continue onward. So if previous, so we take free P and we sign it into the previous P. We say, hey, if there's no free list yet, you could just say, hey, is free list equal null. Then we take the base and we assign it into previous P, the free P, and the base S pointer, so it's going to point to itself. And the base size is, of course, 0. For the previous P, we go to its pointer. This is going to be forever. We say, hey, look at the next element. In the case of base, it's going to say, hey, it's going to look at itself. If the size is greater than or equal to n units, then we basically return it. And if p is equal to free p, we wrapped around the free list. In which case we request more core memory. And we continue looping. Where does previous p get assigned? It doesn't. P gets assigned once. Oh no, no loop condition here. So, okay. We're going to have our free pointer, and then we're going to have our header pointer, and we'll call this thing like what? Current p, which is called p, and previous p. And if free p is equal to null, then okay, we're at the first allocation, in which case we need to set up free p where what is this base thing? Oh, it's just like a thing that we can allocate. Okay. Okay, so free p is equal to null. Then we say free p is equal to a pointer to base, and base dot ptr is equal to reference to base, and base dot s is equal to, yeah, we don't need to set the size. Just say in C23, will this result in base being 0 initialized for all fields? Yeah, okay. So it starts out 0 initialized. We go in here and we just set up its base pointer to point back to itself. And we also set free p to point to itself as well. Okay, so that's just like some initialization stuff. This I don't care about. We'll just say one time init on base slash free p init for. Alright, so now we go into our thing that calculates how many units. And we're going to say forever for now. We're going to check if this section is big enough. This free section. If so, split it and return it. Split it, take the use bits bytes out of the free list and return them. If we ever wrap around to the start, then just request more memory from the OS. So this will be P and previous P, we need to initialize them. So previous P is equal to free P and P is equal to P. P is equal to previous P dot PTR. Sorry, this needs to be a dereference. PTR. Sorry, free P points to the free list. Does free P get assigned anywhere? Interesting. That's not true. I'd rather just see it like this. Okay, so if it's too big, so we have this block of memory. We have a header and a bunch of memory. It has too much memory. So what we want to do is like basically like move the header so the previous place points to the new place. Or we could just take it off the end. It's probably best to take it off the end, that we don't have to update pointers. So that's probably what they're doing here. So you say, hey, the current location size, we're actually going to reduce it by the number of units. So you're smaller now. And then we're going to use those new units. And so to do that, we set our pointer to point to that new location. So we reduced it by size, or reduced it by units. So now the size could be like 3. In which case we need to skip over those 3 bytes, or 3 headers, I should say, because of pointer arithmetic. So we're now pointing to the new location. And then our size is going to be equal to the units. This could have just garbage data in here now. We also need a point to, no, we don't need a point anywhere. It would be nice to null the pointer out, but I guess it's not necessary. And probably a little dangerous. It's not necessary. Can I use code folding here? Yeah. So that's the if block, the entire, so this is a nested if block with an else case inside there. And then our free return is indeed inside the if. And then outside of this, oh, this is where we just advance. Yeah, I think we do need to be in here. So we looped around, in which case we say, okay, P is now going to be more core units. And we'll say if P is equal to null, we'll just return null. Otherwise, we say, okay, should we return immediately from that as well? If P is equal to free P, so we've wrapped around to the where we started, which is the start. This fucking shit, man. It is so not obvious what's going on in that more core function. But it is returning free P itself or null. So it calls break. If break is null, it just, or is errors out, then it returns null. Otherwise, it says, okay, take that memory that you just gave me, but convert it to a header pointer and set its size to be the number of units that was requested. And then we're going to free up +1 which will effectively add it on to the free list. And then we return free P, which is the current place where we're... I don't know why they do that. So basically, we're going to call free inside of this more core thing, which means that free actually does need to come before malloc, because malloc technically has a dependency on free. And then this more core thing. This will be a header pointer. Oops. Units will be just of what size T, I guess. Turn null. Okay. I'm starting to understand this. So we compute how many units that we need in header sizes. We basically this is initialize the base and free P, so that we just took care of that here. This is one-time initialization. And then we go into this loop, and each iteration of the loop, we are advancing through the free list. And our exit condition is that if we wrap around the free list, what do? We add more stuff to the free list. So in this case, if we're at the place where we picked up from, which is free P, free P is always the place where we last read from the free list, basically. So we enter this loop. We initialize P to be our previous, the thing that previous pointer points to, and it's always going to be equal to our free P. So free P and previous P are always going to be equal when we enter into this function. And P is going to point to the thing after the free P, the next value. Because free P was already here. We already considered that in a previous call to malloc. So free P is always basically a value that is the previous pointer, because it gets assigned that way this way, and it gets initialized to basically being equal to the base. So yeah, it's always a value that we're not interested in. We're interested in moving forward. So free P is the previous value always. They call it the start of the free list. It's not even a good name for it. Points to an element of the free list. You can't even consider it the start. So anyways, you go into our loop here. We say, okay, is there enough? The P is now set to a new value. is there enough units for us to actually use this block? And we do that just by checking the size compared to our units. If there's more, then we have to do some work. But if it's exactly equal, we just return that pointer and we're done. But if it's more, then we have to do some math to subtract away the units that we need, update its size and its pointer. Sorry, no, its size. Its pointer we don't care about. But update the new header size and then point to that location. And then we set free P now to say, hey, the previous one I was looking at, that's where you should start next time. And then we return it with the offset of 1. So that's all good. And then if we ever loop back on ourselves, because this thing's just going to loop around these pointers over and over again, like this base points to itself, it's just going to keep on doing that. So if we ever get to that situation, we call more core on the number of units, which actually mutates the free list so that we can then access it. Yeah, more core will modify the free list. But what's interesting is that free P only gets modified here in initialization. Let me just verify that. Free P. So it gets modified during initialization. It gets read from when we call malloc. And then it gets assigned to when we're done searching the free list. So we can say free P points to an element of the free list where malloc will start looking for free memory. Okay. The problem I have with this is that free P is only updated when we discover a new block that we can use. So we've gone around the list, we found a block that we can use, we're going to return it. This more core then mutates this by calling free. And free actually, I haven't looked at it yet, but it mutates the free P down here. So without this call to free, that memory won't be made available. But the problem is that free is going to modify free P, but this malloc, I guess it's guaranteed to be where it started at. So let's see. I gotta think through this. So free P is getting modified by free. So next iteration, we're going to advance to the next element. Free P is not going to be read. If P is equal to free P, well, P is going to get advanced to its next one. But this might actually be, its PTR value might be updated by free P. Let's see. Yeah, here. It's not straightforward. But I'm confident that it's somewhat correct. My implementation. So let's go on to implementing more core. So we got static header. Okay. because it's not exported, basically. That's what that means. And then here, we'll just say if our units is less than n alloc, then nu is equal to n alloc. Or sorry, units. We'll call this min units. Min units, just 1024. Why not? Okay. Okay, so you got min units. Unit set to min units. And then here we call our S break. We say we want NU times the size of header. And that'll give us back our pointer, CP. And we can call that a auto. And to get S break, man to S break, it is Unix standard.h, which we have. But I do need to give it that GNU thing. Forgot about that. Default source. Okay, that'll give us the S break. And then this will be units, of course. Okay. Okay. On error, void star -1 is returned. So we can just cast it like that. So we can say if CP was equal to, okay, void star of -1. Then we're going to return null. Okay. And then we convert this to auto P is equal to CP, but type asserted or casted to a header pointer. We say P size is equal to our units. And they're going to free the up or P plus 1. And the free can take a void star, but we don't need to cast it. And then we're just going to return free P. Okay. So let's go ahead and look at free here. So free takes in the pointer P. We're going to say, hey, P as a header pointer -1. This is the actual header that we're going to point at. I'll call this auto HP for header pointer. And then, okay, so now we got our loop for do we use AP? Sorry, would we use AP anywhere here? No, we just immediately convert it to a pointer to a header. So I'm going to call this thing input P, IP. So IP gets converted into P here. Or base block header. We'll just keep it consistent here. And then P is going to be equal to free P. And then P is going to advance through the list. This can just be a header pointer P. Actually, I can do an auto here, right? No, because we use P elsewhere. Okay, so in here we say if base pointer is greater than P and base pointer is less than PTR. So base pointer, the thing that we're trying to free up here, this is the condition we want to be in. Base pointer is greater than P and less than P. So we're going to go through the entire list looking for that condition. If break, I guess we can do one of these. So if P is greater than or equal to PTR and base pointer is greater than P or base pointer is less than P, oops, PTR, then we break. So this is basically saying find where free memory goes in the free list. So here we need to say, okay, base pointer is greater than P or base pointer is less than same condition here. So the base pointer is greater than P. So you have base pointer, which is like where our memory that's being freed is located. And we say, okay, if it's greater than P, so we're ahead of P, and we're below its next element, then we're in the right location. So that will get us out of here. But then we also say, if that's true and P is greater than or equal to P pointer, which means that we're pointing backwards, then we break. I don't understand how that happens. So base pointer is greater than P, and base pointer is less than P pointer. Okay. So that means that we're in between the two nodes. And P is greater than or equal to its pointer. I don't understand how that could ever happen. Here you're saying P less than BP less than P pointer. There's a certain ordering to this. Oh, but these are equal. You can say they're equal. Okay. No. Because these aren't equal. These are strictly one element after the other. Landed here awake for why your head is so ethereal. I don't know, is my camera messing up? Oh, just the light coming in. Sorry, I'm like wrapped around the axle on this free implementation here. Trying to figure this thing out. Ugh. Do people actually just like get this stuff immediately? Because I mean, I get stuff immediately when there's good comments and like, you know, it's like pretty obvious, you know, based on context, like what's going on. But when you have all this like pointer arithmetic and all these like really terse expressions that like have single variable or two character variable names, it's like so... It's almost like the authors just wanted to make the code as few characters as possible and obfuscated it in doing so. I mean, this isn't even that long of a function, but it's still like, okay, so we start our at the beginning of the free list. We advance through the list. This is actually relatively straightforward. And at any time when we are strictly in between two pointers, we exit this function. Because that's the condition here. But then there's this other weird frickin' condition here. I don't even understand why this exists. They're saying it's because it's at the start or end of the arena, where not only do you have to be strictly, but you also have to be in this situation, which I think is impossible. But whatever, I'm just going to move on because I don't want to get too wrapped around the axle on this. Maybe the text will explain why that happens. So then there's an if else here, and then another if else down here. Another thing I don't appreciate with their style is not having the curly braces around some blocks and having them around others. It's like, dude, like just put the braces. If you're gonna put the braces, put the braces. And at the end here, we say free P is equal to P. Okay. Let's see. If BP plus BP plus BP size. So this is taking the base pointer plus its size. Wait a minute. Okay. So this is basically pointing to the next memory location. So if that is equal to or PPTR, then the memory next to us Just say ahead of this location is contiguous. Merge. I don't know if that's how you spell that word. Contiguous. I think it is. Yeah. All right. So the memory ahead of us of this location is contiguous. Merge. Otherwise, it's not. In which case, we just say, hey, BP, you're just going to point at it because it's too far away to merge with. So PTR. We're saying, hey, P's PTR. So it's next element. I really feel like we should have called this thing next instead of PTR. Let's do that. I'm going to rename this thing. If I go here, I think I do code rename and just call this thing next. Yeah, I think that'll add some clarity here. So you're saying our next element in the free list is going to be the P that we found. It's next. Wait a minute. Did I do this wrong? I think I did it wrong. That would be this case. So I did read this wrong. So that's what I thought. It would just be next. So this thing is now going to be, okay, BP size is going to be plus equal to P next size. I can do dot size here. Yeah. No, I can't. P next size. And this needs to be plus equals, not just plus. Okay. And then we handle the lower bounds as well. So here is the memory behind this location is contiguous merge. So that's going to be P plus P size is equal to BP. And then in here, we're going to say P size is going to be plus equal to BP size, and PTR is going to be equal to this PTR. Okay. Sorry, P next, I should say. Let's rename that. Else P next is equal to BP. And then P will be the previous value of free P. So when we, oops, so I didn't do plus equals, I didn't do equals there. So at the very end here, we're guaranteed that free P is going to be equal P, which could be either the merged left-hand side, I'll just trust that it works. Let's go ahead and run some tests here. So we're going to call malloc, and we're going to print out its pointer address. And then we're going to free it. Free p. Make, oops. Free. Here, this thing is called on free. Free is defined up here. That should be fine. Malloc is a function that you call to allocate memory. So it's like memory allocate. If you do man3 malloc, this is the man page for it. It comes with a bunch of other functions, but the main one is free. So when you call malloc, you ask the operating system, give me this many bytes of memory, and it gives you back a pointer. And this is in libc. Free is the inverse of that, where you give it the pointer and it gives the memory back to the system. And then calloc is these are just variants of malloc, basically. Void star is the memory location that malloc returns. And I'm trying to create my own allocator here. The allocator uses sbreak to do its allocations. That's not the way most allocators work in modern days, because this book is really old. But I want to do it just as an exercise. So here, note returned from sbreak. I don't understand what that means. Sbreak unit size of header. All right. So we got our allocator. So it's basically just reusing the memory, which is kind of nice. That's what we want. Let's do it by units of 10. We'll do it by units of 512. So I will be I times 512. There we go. And if we pipe this into awk, let's see if any of these memory addresses are being reused. Awk. We'll print out $NF 0, 1, 2, 3. I think it'd be 3. It's going to standard error, that's why. So we do 2 and 1 here. There we go. And if we do a sort, and then you do unique C, so they're all unique addresses. Let's try a smaller value then. Let's do like 5. So I did 512. Let's do 256. Same thing. We're getting new addresses each time. Let's do 128. Oops. Okay. And if we did just I, like we were doing before, yeah, we got a lot of address reuse for small elements that can fit into the existing allocations. Okay, it works. Happy with that. I mean, I didn't verify it fully, but let's go ahead, pull up the code here. What do I want to do? Oh, I wanted to run it on a 32-bit mode as well. So if we run it under 32-bit mode, less reuse, but still a good amount of reuse. Okay. I really like this. I found this align as, I think it's a operator in C now. And it also uses this thing called FAM, which is, I forget the name of it, but it's basically like an array at the end of your struct that has no length. Like, it doesn't contribute to the size of the struct, but it forces this line here basically forces the alignment of the struct, and then we assert that down here, the static assert. Man, I need to do more algorithms work. I feel like a lot of this stuff, like I've grappled with a little bit in the past, but it's just starting to feel like I'm a little rusty. All right, let's go ahead and read the rest of the text. So the function more core obtains storage from the operating system. The details of how it does this vary from system to system, since asking the system for memory is a comparatively expensive operation. We don't want to do that on every call to malloc, so more core requests at least n alloc units. This larger block will be chopped up as needed. After setting the size field, more core inserts the additional memory into the arena by calling free. The Unix system call sbreak n returns a pointer to n more bytes of storage. Sbreak returns -1 if there is no space. Even though null would have been a better design, I guess there's a note here around using sbreak. To do, how do you ensure that this location is aligned properly? I guess because we're requesting the number of units, and each unit, it could be unaligned. Could sbreak return a pointer to a byte location that is non-aligned? And then we just assume not aligned. We'll just do a question mark there. I think it could. Let's continue reading. The Unix system call sbreak returns a pointer to n more bytes of storage. Sbreak returns -1 if there's no space. Even though null would have been a better design, the -1 must be cast to a char star or void star like I did. It can't be compared with the return value. Again, casts make the function relatively immune to the details of pointer representation on different machines. There is still one assumption, however, that pointers to different blocks returned by sbreak can't be meaningfully compared. This is not guaranteed by the standard, which permits pointer comparisons only within an array. Thus, the version of malloc is portable only among machines in which general pointer comparison is meaningful. Free itself is the last thing. It scans the free list starting at free P, looking for a place to insert a free block. This is either between two existing blocks or at one end of the list. In any case, if the block being freed is adjacent to either neighbor, the adjacent blocks are combined. The only troubles are keeping the pointers pointing to the right things and the size is correct. Although storage allocation is intrinsically machine dependent, the code above illustrates how machine dependencies can be controlled and confined to a very small part of the program. The use of type dep and union handles alignment, given that sbreak supplies an appropriate pointer. Casts arrange. See, they just called it out here. Like, he's saying it handles alignment given that the sbreak gives us an aligned pointer, which I don't know if it's going to be aligned. Let me ask ChatGPT, see if it knows. The pointer returned by sbreak, is that certain to be aligned? But only to max align T, effectively not arbitrary large alignments. With the standard guarantee, sbreak is not part of ISO C. It's a POSIX Unix interface historically so-and-so. On typical Unix systems, program break is page aligned when the process starts. The kernel grows the heap in page size chunks. The pointer returned by sbreak will therefore be at least page aligned at the moment the heap grows. However, you can sbreak 1 and advance it by 1. P2 is not guaranteed to be aligned. It's just a previous break value. So the guarantee, apparently sbreak starts aligned but can get unaligned by, is that 1L? I think it's 1L. Unaligned by oh. Okay. So casts arrange that pointer conversions are made explicit and even cope with a badly designed system interface, even though the details here are relatively related to storage allocation. The general approach is applicable to other situations as well. The standard library function calloc n size returns a pointer to n objects of size with the storage initialized to 0. Write calloc by calling malloc or by modifying it. Then malloc accepts a size request. Malloc accepts a size request without checking its plausibility. Free believes that the block it is asked to free contains a valid size field. Improve these routines so that they take more pains with error checking. I don't really care about error checking. Calloc might, Write a routine be free that will free an arbitrary block P of n characters into the free list maintained by malloc and free. By using be free, a user can add a static or external array to the free list at any time. Okay, I might come back to these exercises. I'm going to highlight them because they do seem a little bit interesting, but not terribly at the moment, mainly because I just got done with this thing. So that is the book. That is everything except for the reference manual appendice. I've been streaming for 4 hours. I really didn't. I don't know where the time went. It's been 4 hours of. Wow. 4 hours of focused labor on this thing. I'm going to go ahead and commit it. We'll go ahead and do a make one more time, because there are some warnings. We'll do a make clean. Oops. Make. And we'll do a build allocator. allocator 32. Okay. What's this temp file here? I can remove that. Okay. Spin up a readme. So that was chapter 8. Okay. Git push all. We're done with that bad boy. I did want to, informally just go through the reference manual real quick. I'm not going to go in deep reading here, but I did want to just look through some things. Let's do through the keywords. It's always nice to do. So auto was repurposed for type inference in C23. So on my own VM, Omarchy was not working because my GPU doesn't support 3D as it's an old graphics card, NVIDIA 2010 or NVIDIA 210. That sucks. Yeah, I mean Hyperland might require some type of hardware acceleration. Yeah, most chips nowadays, like the CPUs themselves, come with graphics capability to be able to handle some of this stuff. So even if you have an old GPU, your CPU should be able to do it. But if you're doing it through a VM, that goes through a hypervisor, which basically the hypervisor would prevent Omarchy from accessing those capabilities in the CPU, most likely. I would try dual booting. Have you ever tried dual booting? Where you just create a partition for the installation. And actually, dual booting is a little bit more challenging with Omarchy because Omarchy requires the entire disk to be encrypted. So if you were going to dual boot, you would have to have a separate hard drive, a separate NVMe SSD or spinning hard drive. Yeah. I would try dual booting if you can get away with it, but don't install Omarchy on a partition, because basically I tried doing that when I first was experimenting with Omarchy, and the installation deleted everything. It basically said, screw your partition, I'm taking over the entire hard drive. And it wiped and encrypted the entire hard drive, which is not what I expected. All right, so let's look through the keywords here. So auto, break, case, char, const, continue. These are all pretty basic. Do, I'm not familiar with do. Let's ask AI. What is the do keyword in C used for? Oh, the do while loop. Okay. Double, else, enum, extern, float, for, go to, if, int, long, register. Okay. What is the register? I think I already know this. It's a hint to the compiler to store the value in a register, but it doesn't have to be respected. Yeah, no problem. Okay, so return short signed size of static struct switch type def union unsigned void volatile. I guess we can do it with a refresher on volatile. And what does the volatile keyword in C do? The object can change. I think it disables optimization. Yeah, do not optimize access to it. When a variable is declared volatile, the computer can't perform the real load. Always performs a real load store, no caching, and registers across access. Does not eliminate seemingly redundant reads and writes. Does not reorder access to that specific volatile object. It does not make operations atomic, provide thread safety, create memory barriers. I think most atomics are also marked as volatile, though. Create memory barriers, prevent reordering of non-volatile operations around it, except as constrained by observable behavior rules. Why it matters mainly for memory mapped I/O hardware registers. So you got a volatile uint32T. We don't want that optimized away. That makes sense because it could. This is like a pointer to a place in memory, and we want to be actually dereferencing that memory over and over and over and over again every time we check in this loop. Without volatile, the compiler might load the value once, assume it never changes, turn the loop into an infinite loop. Signal handlers, yeah, when you're using sig atomic T. Allows you to share between the handler and the main thread of execution to avoid the compiler caching flag. Set jump and long jump. Local variables that must retain values across long jump sometimes need volatile. Okay. Yeah, let's read what it does at the assembly level. Without volatile, while flag is equal to 0, the compiler might generate move flag into EAX, test at EAX and EAX, and then jump equal to the infinite loop. With volatile, it must reload each iteration. So flag is red. Jump equal to loop. I don't know about this. So how many people in 2026 all over the world are learning the C language? Probably a good amount. I was talking to one of my friends about this language popularity index. There's like the Toby. And if you look here, whatever. It's number 2. This year, the C language got up to number 2 in popularity for programming languages, just under Python. And Python's implemented in C. So one of my friends was saying, like, oh, people don't really write software in C anymore. It's like, dude, like everything you use is implemented in C. Like all of your operating system stuff, like everything. What I would say is that C is not a popular language for good reasons. It's not a popular language for application development, but for library development, it certainly is very popular for all systems programming stuff. It's very popular. Embedded programming is very popular. Like there's a lot of code out there that's in C. Like, and like, even if your language isn't implemented in C, which most programming languages are implemented in C, even if that's not the case, everything interops with C. It has some type of like foreign function interface with C. It talks to C ABI. So if you're talking between like, say, JavaScript and Python over the actual like address space, like not over a network, then you're most likely talking the C ABI if you're making calls between the two. Although Learner these days are just building apps via integration APIs in Nest.js or Next.js, probably by AI, that's all an act like Einstein. Yeah, I mean, I don't really give a shit. Like, I know a lot of people are going crazy right now over the AI stuff, and I think it serves a purpose. Like obviously, like I'm learning about some stuff right now using volatile from AI, but like I don't know. I saw this one guy who is like orchestrating like dozens of like Claude code things, and like I'm just like, I mean, if it works for you, it works for you. But at the end of the day, these things have to produce code. And I understand like you're not going to be reviewing the code because you've given up on that because you're not good at programming. But to build reliable software systems, like for the time being, we still need human beings in the loop to evaluate the output of these models. Like it's not going to be like magical AI solves all of the software problems. At least not yet. Like maybe down the road that we get there, but I don't know. I don't see it right now. What I see is AI creating a whole shitload of security vulnerabilities and reliability issues. I mean, Claude and OpenAI have had so many outages themselves, and it's like, well, you figure if AI was going to be the panacea for reliability, these AI companies would be the first ones to adopt it for that purpose. And yet they're still having reliability issues. So I think reliability is still going to be an issue in the post-AI world, as well as security. Like these AIs are not, I would say AI is a net negative for the security of software systems, because it enables more people who have no fucking clue what they're doing to ship stuff into production. And that's not to belittle people who are like new or whatever to building stuff, but it allows for more people who literally have no business shipping stuff into a production environment to do so. And maybe that'll necessitate a lot of change in the industry to make it to where we can have these models churning out stuff in a secure way. But I think for the time being, it's just going to be a nightmare for security. And the open claw stuff, like I want to play with that. I think it'd be fun to play with, but it's just like, I don't want it to have access to my stuff. Like I genuinely just don't. I think it's navel gazing. I think it's like kind of like, I don't know. If I need to send an email, I'll just send an email. Like I don't need it to send an email for me. Like I don't need to have it to have access to all my email to send an email for me. I don't know. I think there's a productization of AI that I could use to help make my life more efficient, but OpenClaw isn't it, for me at least. And all I see is like people opening up their entire world to this thing, and it's just like, really? Okay, more power to you. Thanks God, now I have more jobs to secure. Exactly. It's going to be a great thing. AI security, I guarantee you in 6 months, it's going to be like the next big thing where people are talking about how, oh, we got all these AI products out there doing all this stuff. We need to wrangle them in and secure them. And it's like, but if these companies want to pay money to have people secure these AI systems, like, okay, let's do it. I think it's always better to be on the offensive side of security than the defensive side, especially in this modern time with all this AI introducing exploits and vulnerabilities in their software. Like, you want to be on the attacker side, like being defensive in security, like protecting systems. I don't understand why anyone would ever want to do that. It's a nightmare. I mean, I have had that type of role in the past, or a similar type of role where you're playing defense. But the best thing to defend against attacks, cybersecurity wise, is to have a system that does nothing. Like having fewer ports open on your firewalls, just blocking traffic everywhere that is not necessary. Like taking things away is what makes them more secure. And the most secure system is a system that does nothing. And these companies want to have systems that are doing everything. And it's like there's a tension there between having AI systems that are super flexible and able to do everything for you and actually having some guardrails of security around that. And doing that type of defensive work, I just think it's kind of like, it's frustrating because you're constantly battling internal forces in the company that want to grow the business and build new products, which is great for the business. But it's a cost benefit trade-off constantly. And there's never going to be like a thing in AI where you just say, AI, make it secure. Like, it's just not going to happen. So I think there's going to be a lot of opportunity for people, especially on the offensive side, the attacking side. Like if you're developing exploits for systems, like in an ethical way, obviously, ethical hacking, I think you have a lot of fertile ground to find exploits in now. Whereas in the past, well, I guess in the past it hasn't been too bad, but it's getting even better, I should say. AI help a lot in terms of learning. Yeah, I mean that's kind of the way that I've been using AI, is that it's been a really great learning tool for me to accelerate my learning. Whereas sometimes, I'll have a thought and I'll be like, oh, I wish I could ask a seasoned professional, like this question. And in past parts of my career, I've thought back to it, and it used to be search engines were so freaking good that you could get answers to those type of questions. I mean, not in like a prose written specifically for you, but you could get to where you needed to go on the internet so quickly. And what I realized is that when I was early in my career, I had access to a search engine that was really awesome. And then over the past 20 years, search engines have just gone to shit. And so AI is now this new feature that's really just, it's bringing search engines back to where they used to be. Like I know people don't think of this way, and it's kind of like a boomer way of thinking of it, but I think of AI as just like really great search. I mean, obviously it's more than that, but it's one aspect of the tool is like a really great search, and it's valuable because of how shitty search engines have gotten. Well, the market right now in terms of defensive is you just use tool and you know nothing. Exactly, yeah. Okay. So we finished this book. Yay. I've been thinking about what my next book should be. So I have this new learning repo. I don't know if you saw this, but it has everything in here. So these are all the books and talks and blogs and courses and everything that I'm interested in right now. And I put these SRE books at the top of the list, but I'm wondering whether that would be helpful. There's also this book, Cracking the Coding Interview. I've had it on my bookshelf now for like over a decade, and I haven't read the whole thing. So I've been wanting to get to that. I think that might be useful for like problem sets and interview prep. Well, what I like about AI is that when in the past I want to ask something from someone, you have to find people who were good at that. Yeah, exactly. Or have basic knowledge more from you. Now I totally agree with you. It's kind of like talking to a consultant who is giving you free sessions prior to the implementation. Exactly. Yeah, I mean, we'll see how far this goes, but my suspicion is that like a lot of these tools, they're going to accelerate people who are currently bandwidth constrained on like learning. And that's the way I'm using it. I'm using it as a tool for learning. But if you're pursuing building a business, like I'm sure it's going to help you with that. But is it going to be a thing where you just like one shot an entire application? I don't think so. I mean, I've had friends tell me that they're able to one shot GUI applications for the Mac, and they showed me a few of them, and it's impressive. I'm not going to, not give them credit. I think it definitely is impressive what you can do, but to create a product, you're never going to one shot a product. There's always going to be need for someone to go in and at least tell the AI what needs to happen. Because the AI just gets off track so easily. Did you see that compiler that was written by Claude? If you go to, it's like a Claude C compiler. Yeah, this guy here. CCC. First of all, I take offense to the name here because this is Chaos Computer Conference or Congress. C3. Oops. Communications Congress. This is the CCC. I've never been here, but they produce a lot of really good conference talks. Have you checked out their conference? You're into cybersecurity. Chaos. I think they're YouTube. C3. Yeah. Not C3 Church. I think Chaos is like a hacking group or something in Europe. You don't know about them? Yeah, they do a lot of really interesting stuff. So I think their recent one was, 39C3. CCC.de. CCC.de. Some of it's in German. Chaos Computer Club. That's what I thought it was, but it's Communications Congress now. What's this guy here? Oh, there's one on Asahi Linux. Is there volume on this thing? Oh, there it is. Sorry, there's latency. Porting Linux to Apple Silicon. I gotta work on the latency because, like, when I move here, it shows up immediately on my pretty much a small amount of latency. It shows up on my OBS, but when I play audio, the audio takes forever to get to the streaming box, so I need to look into that. But yeah, they have like a lot of talks here. Some of them are better than others. Let's just rank by popularity. So that was 11 years ago. That's a little too. Let's search for CC3 conference. I think it is that media CCDE, but is this the one the Cory Doctorow gave? Yeah. C3 Cory Doctorow talk. Yeah. This one here. Post-American shitification resistant. That was an interesting one. Some of it's in German, so might not be super accessible. Anyways, the K&R C compiler, this thing, like, again, it's impressive, but maybe we should pull this down and play with it. I'm not that interested. Okay, so I guess next book. Let's bust open this README. I'm gonna mark this as complete. That was a fun book. So the next book I was thinking about reading is the 2 SRE books. One of them I've read about half. Again, this is like me cleaning my bookshelf off. I read about half the book and then I gave up on it. That's this book here. The workbook, which is a companion to it, it's about of equal size, has a lot of war stories from Google. Those 2 books together, it's about 400 pages each, I think. So I think it's about 900 pages total. So it would be a pretty long project to get through those, maybe like a month. Yeah, it's all going to GitHub, and then I also, let me actually make a change here. Let's say finish K&R C. Git push all. So I'm also pushing it to Codeberg. So my whole deal is I hate Microsoft. And so Codeberg is where I'm going to be pushing stuff. I'm going to push it to GitHub as well. So if you go to GitHub, it'll be showing up here. I got this new repo called LearnLog. So yeah, it'll go to both. I like Codeberg better though. The activity graph on Codeberg is actually based on the times and dates that you perform the activities. Whereas GitHub's you can kind of trick out because their activity log is based on commit activity, not push, like the times when the commits were pushed. That's why I don't have any history here. So I'm going to start the C programming language. Awesome. From your YouTube videos. Okay. I'm learning a lot from these streams, a lot. That's great. I'm glad you're getting something out of it. I had a lot of frustrations with this book. But yeah, if you encounter anything that you have any questions about, I'm more than happy to like take time to like chat about it, come back to it, revisit it. Sometimes I wonder like if these streams are super helpful for people or not. But at least there's you that gets some value out of it. I was thinking about doing some more recorded videos on different topics and getting like a little bit better at publishing YouTube videos. Because like right now I'm just like recording random things that I think about. But it would be nice to say, I had an idea today about something to record a video on. What was it? Well, they are awesome. Yeah, something about operating systems I was thinking about today. It'll come to me. But there's a bunch of ideas I have about videos that I want to do. And I think writing it out as a blog post up front too would not only give me the time and space to like get the ideas kind of like worked through my head, but also like give me like another medium to like publish, and then do a video as a companion to the blog post. So like communicating these small ideas or bite-sized ideas do the writing to make sure that everything's clear, and then actually do multiple takes and like do like an actual polished video. I see a lot of people on YouTube doing these type of videos, and they're heavily edited and polished. I don't think I want to get super polished, but having a little bit better presentation and getting better at presenting topics in a way that people can understand, getting better at communicating. I think those are all skills that I want to like further develop. So I might put some more effort into that. Why not plan a complete series on YouTube about problems and also create your own blog posts? Yeah, I mean, the blog posts are definitely something I've been thinking about. Why not? Yeah. Well, I'm not going to say this. Your videos have way more content than another streams and videos. Yeah. I wonder how much longevity I can get out of doing the reading streams, because I talked to some of my friends about it and they're like, that sounds like the most boring thing ever. Like, I think the audience for reading like actual books in a streaming format is limited. But then I think back to like the ultra learning dude, and he does live streams where he just does learning. This guy here, I forget his name. What is his name? He had a blog, Scott Young, this guy. And I'm pretty sure he's done like streams in the past. Scott Young, Ultra Learning, Twitch. I guess he's not on Twitch. Oh, other people read on stream. These books I've read or am reading on stream. Finished Systematics by let's check out this guy. Oh, there's an about page. That's what I was looking for. Proceed. Zoom out a little bit. Home, videos, schedule. Oh, this is the mobile site. Okay. See, these little things here, I remember these being a big thing back in the day on Twitch. Maybe I should have something like that. But I guess other people stream reading on Twitch, so I wouldn't be the only person. Twitch.tv about. Yeah, mine just has the links here. I need to like have those little things below here. People do read on streams, but they don't about computers. Interesting. Maybe that's my niche that I need to exploit. They're called extensions. Yeah, I think I saw them in the UI when I was setting things up, and then I just didn't have the patience to like actually do it. But yeah, if you're on Codeberg, you can drop me a follow on Codeberg. I don't think I have any followers yet. Let me see. Yeah, I got 0 followers. You could be my first follower. Codeberg seems to be like the cool place. It's like a 501c3 nonprofit. If you go to explore, you can see all the projects that I started pushing to Codeberg. It's like a lot of stuff. Let's sort by most stars. I know Zig has moved to Codeberg. That's the reason why I went. Yeah. Zig is like the big project that's moved over there. Zig had this huge blog post on why they moved. Zig, Codeberg, GitHub. Yeah. Migrating from GitHub to Codeberg. I think Andrew Kelly had a blog post. Inexcusable bugs. Yeah, this is the safe sleep thing. All right, let's get some more reading done on the reference. I'm just gonna skim through this. What time is it? It is coming on 5. I do want to break for dinner here at some point, but I want to get through some of this reference. So we were talking about volatile, exploring why it exists. Basically, it disables optimizations in the compiler so that it doesn't optimize things a way that you might otherwise need. If you sum up the complete book in Excel, draw how are you gonna in 10 minutes? What do you mean by that? Can you explain what you mean by that? Because I don't quite understand that. Integer constants, character constants. This is all nothing new. Floating constants, lots of constants, enumeration, string literals, syntax notation. Okay. Meaning of identifiers, storage class. This is actually something I think might be helpful. I've come across a few times now. Let's read about storage classes. There are 2 storage classes, automatic and static. Several keywords together with the context of the object's declaration specify its storage class. Automatic objects are local to a block. You never have a storage class listed on a variable as automatic though. And are discarded on exit from a block. Declarations within a block create automatic objects if no storage class specification is mentioned. Yep. Or if the auto specifier is used. So that's where the auto specifier has changed. Objects declared register are atomic and are, if possible, stored in fast registers on the machine. That's not true anymore, that they're not atomic. Oh, sorry, register. Sorry, I thought that said volatile. Static objects may be local to a block or external. So this is actually going through and saying what these different things are. So static objects may be local to a block. Sorry, I missed your chat. Means sum up the C learning slope with a flow, what you learn new and evolve in this book, but with a diagram in Excel. You mean Excalibur? Yeah. Yeah. I was thinking about doing that, like at the end of every book that I read, just like give like a quick 10-minute summary of things that I learned and whether I would recommend the book or not to people. It seems like a lot of work though. Maybe I should just like do it. I mean, I've completed 2 books now. One was a 1,400 page big boy. This one's only about 200 pages, not even. So I've read total on stream approximately about 1,800 pages of highly technical operating system and systems programming stuff. So it might be useful to do a review at the end. sometimes I finish these books and I'm like, I don't want to even think about any of this stuff for like a month. All right, let me kill this. I just wanted to read about the static objects here. Static object may be local to a block or external to all blocks, but in either case, retain their values across exit from the reentrant exit form and reentry to entry from and reentry to functions and blocks within a block, including a block that provides the code for a function. Static objects are declared with the keyword static. The objects declared outside all blocks at the same level as functions are always static. They may be made local in a particular translation unit by use of the static keyword. This gives them internal linkage. They become global to the entire program by omitting an explicit storage class or by using the keyword extern. This gives them external linkage. So you have to extern your globals if you want them to be linked. Okay, let's continue on here. Nothing really interesting here. So does going to university back then help a lot in terms of learning? My university, my time at university has been, periods of it were really helpful, and then other periods were not helpful at all. If I could go back in time and redo it, I would just spend that time doing my own learning. I wouldn't pay the money to go to college. And I always told myself I'm going to get a piece of paper so that I have the credentials to pursue my career. And it turned out none of my employers that I got hired by even knew that I had a degree. Some of them were like, "Oh, I didn't even know that you had a degree." It's like, in this day and age, I feel like there's so much resources out there. Like even when I was in college, you could go to MIT Open Courseware. There's just so much free educational material available. Sorry, move that. So what are we interested in here? Actually, you know what? I'll just full screen it. Search for software engineering. And resources. Lecture videos. These are always helpful. It's probably best to go here, clear the search, clear all, computer. Yeah, here we go. A gentle introduction to programming using Python. Let's search by like, is there like popularity? Let's do let's do graduate. Why not? Oh, here we go. Computer science. Some of these are graduate. A lot of Python stuff. I would say MIT is a good thing. MIT Open Courseware, but then, I mean, Stanford. Here it goes. Free online courses. Engineering. Let's see. Topic: computer science, cybersecurity. You're interested in cybersecurity. Bam. We don't want any of this stuff. Civil. Get out of here. Reset filters. Oh, they got a glitch. Alright, let's reload. Advanced Cybersecurity Program Preview. Ooh, sneak peek. I like going to the YouTube channel. Andrew Ng, I remember he did a bunch of stuff on, bunch of lectures on machine learning. Let's search for security. AI security. 4 months ago. This is like bleeding edge. You got AI and cybersecurity with Sam Altman. That guy's such a tool. But yeah, there's lots of resources online nowadays. I feel like going to university doesn't really make sense. Yeah. Cool. All right. Yeah, I think I might take a break too here and get some food. I'm starving. But I'm going to hop back on probably in an hour just to review some of the reference manual here and just make sure that we don't miss anything in the reference manual that wasn't covered in the book. And then I might do some work on the allocator as well tonight, depending how I feel. We'll see. We'll see what inspires me. Cool. All right. I'll be back and streaming it on in about probably an hour and a half. Cool.